This video will cover Chapter 8 from the Gabrosek Stephenson textbook. So Chapter 8 is a little bit different than everything we've talked about up until this point. So before we jump into Chapter 8 material, a little bit of review. If we wanted to compare two means statistically, how could we do that? Well, there's two things that we've done over and over and over in this class. Confidence intervals or hypothesis testing. So what we talked about back in Chapter 6, where we talked about the difference between two population means. We could do a confidence interval on the difference between two population means. We could do a hypothesis test. So we know how to do that. If we wanted to compare three or more population means statistically, can we use the same format? And the answer is, well, kind of. But we would have to take them two at a time, because when we're talking about the word difference, you can only find the difference between two things. For example, if I ask you to find the difference between the numbers 2, 4, and 32, well, we can find the difference between 2 and 4, we can find the difference between 2 and 32, and we can find the difference between 4 and 32, but we can't find the difference between all three simultaneously. So if we have three different groups, then we can do that with three comparisons. We can compare group 1 to group 2, group 1 to group 3, and group 2 to group 3. If we add a fourth group to that, that makes it 6 comparisons. If we add a fifth group, that makes it 10 comparisons. And if we had a sixth group, like if we wanted to break data down by your favorite color, for example, that would be 15 different confidence intervals or 15 different hypothesis tests that we would have to do. That sounds like a lot. We probably don't want to have to do all of that work. There's got to be a better way, and there is, and that way is called an ANOVA, which is a short term for analysis of variance. And what an ANOVA does is it allows us to compare three or more population means simultaneously. So it'll run one test, and it'll check if there are indeed differences between our population means. In a little bit, we'll talk about the nitty-gritty details about it, but for now, what you need to know, our F statistic, our test statistic that we are calculating in our ANOVA, is basically a division problem. It takes the variation between the groups and divides it by the variation within the groups. The variation between groups is 0 if all k of the sample means are equal, and gets larger the more spread out the sample means are. If we think back to Chapter 6 material, where we had height broken down by class standing, if freshmen average 67 inches and sophomores average 67 inches and juniors and seniors all average 67 inches, then there would be no variation between the groups. Now, that's not exactly the case. There is some variation, so our numerator will kind of quantify the differences that we see between the groups. The variation within groups, our denominator. The variation within groups is 0 if all members inside each distinct group have the same value, and get larger the more spread out the data within each group is. So, again, using the height broken down by class standing, if all freshmen were exactly 64 inches tall, well, then there would be no variation within that group. Now, that's not the case. Students come in all different heights, whether you're a freshman, sophomore, junior, or senior. So there is some variation between the groups, but there is also variation within the groups as well. So we can at least continue with calculating our F statistic. So there is another hypothesis test that's working behind the scenes here. I skip over step 1, your assumptions and conditions. We're dealing with means again, which indicates if we don't have normal data, you need to make sure you have at least 30 from each group, and we have to have a random sample. So standard stuff for whenever we're talking about means. Step 2, formulate your hypotheses. So if I take you back to Chapter 6, where we talked about our null hypothesis there, we used mu1 equals mu2. Well, we are just going to extend that here in Chapter 8. Our null hypothesis will be mu1 equals mu2 equals mu3 all the way up to mu sub k. So however many groups you have, all of the population means are equal, which is what we can write that out using words. Now our alternative hypothesis here is going to be every other possible outcome. Well, if someone asks you to describe everything that isn't something else, you just throw the word not out front. Well, we want to consider ones to be success and any other number to be a failure. Well, you could say, well, if you roll a 2, 3, 4, 5, or 6, or you could just say not rolling a 1. So that's the idea behind here. Either all the population means are equal or not all the population means are equal. Unfortunately, there's not a shorthand notation to write our alternative hypothesis here. We could say like mu1 doesn't equal mu2, or mu1 doesn't equal mu3, or mu1 doesn't equal mu4. And, well, we don't want to have to do all those because then we're back to doing all those different comparisons that we said we didn't want to do. If we have 6 groups, we would have to write out 15 different comparisons. The note that I have attached here, which it looks like I forgot to fill out, only one mean needs to be different. So only one population mean needs to be different for our alternative hypothesis, so for H sub A to be true. So we only need one difference to exist in order for the alternative hypothesis to be true, because either they are all equal or they're not all equal. At least one difference exists. So we will not write out our alternative hypothesis using symbols here. The example that we'll use, is it true that the best students sit in the front of a classroom, or is that a false stereotype? If we were in class, I would ask the front section if that's true. They might say yeah. The back section, well, they might say yeah too. But we're going to run some numbers to see what we can say here. In surveys done in 2 statistics classes, students reported their GPA and also answered the question, where do you typically sit in the classroom? Front, middle, or back? And then over here, we've got a bunch of information that can all be found from the Explore option. We have the 3 different locations that people can sit. We have the individual sample sizes, the individual sample means, and the individual sample standard deviations for each one of those groups. A little bit of notation that is specific here to Chapter 8 material. K is going to be the number of groups, which is why up here I went ... mu sub k, because k will be the number of groups. X sub I bar, S sub I, and N sub I are going to be the sample mean, the sample standard deviation, and the sample size for the ith group. And what I mean by that, X1 bar is the sample mean for group 1, N2 is the sample size for group 2, and S3 is the sample standard deviation for group 3. Big letter N is our total sample size, which means SPSS is technically wrong in what they use, and we should change that to a little letter n because these are individual group sample sizes. But big letter N will be the total number of students regardless of where you sit. So from our table here, we can see that there is variation between the groups and there's variation within the groups. We can see that there's variation between the groups because not all of the sample means are equal. The sample mean for those that sit in the front is a little bit higher than those that sit in the middle, and that's a little bit higher than those that sit in the back. Also, we know that there's variation within each group because our standard deviations are non-zero. I'm not saying that everyone that sits in the front gets a 3.2 GPA. I'm not saying that everyone that sits in the middle gets a 2.98. I'm not saying that everyone that sits in the back gets a 2.92. There's variation between each group. There's variation within each group. And we need to check those differences to see what we can say about the populations as a whole. So we're just going to jump right into our SPSS output here. The first couple things I want you to notice, we have our F statistic, so that's your answer to step 3, and we have our p-value. After all this time of SPSS calling our p-value asimp sig or something along those lines, finally they're like, okay, yeah, we know it's a p-value. So here the important thing is our p-value is 0.001, which is really, really, really significant. It is much less than 0.05. So we have a ton of evidence to reject the null and accept the alternative. So to this point, the only thing we can really say is not all population means are equal. I'm not saying smart people sit in the front. I'm not saying dumb people sit in the back. Our only conclusion to this point is not all population means are equal. What I usually do when we're actually meeting in class is we'll end up filling in all of these, and then when we're done, I'll be like, yeah, everything that I told you is already in this table down here. So don't feel like you need to copy everything up there, but I'm going to let you explain a little bit of what's going on here. So this between groups, up above, you see the word location. The reason why it's called location is because the name of the variable of where you sit in my classroom, or not my classroom, but where you sit in the classroom, that's called location. That's why you see the word location up there. Our degrees of freedom equals k minus 1. So we have 3 different groups, which means our degrees of freedom on our location is 3 minus 1, or that's 2. Our sum of squares for groups. Well, we see the word sum, so we're going to add up a bunch of things. We see a square, which means we're going to square something. Out front, we have n sub I. This is more of a scaling factor. The reason why we have to take that into consideration is if we go back up to our data, the fact that the vast majority of people say that they sit somewhere in the middle, their collective information should mean more. So we do multiply by n sub I in this formula. And then we take x sub I bar minus x bar. Inside the parentheses here, we are figuring out how far each individual group's sample mean differs from the overall sample mean. So if we go back to where freshmen, sophomores, juniors, and seniors all average 67 inches tall, well, then all of these values will be 67 minus 67, and those will all go to 0. If that's not the case, if freshmen average 5'2" and sophomores average 6'2", and juniors average 7'2", and seniors average 8'2", it's not the case. But if that were, then all these values would be really large. Once we square them, they become even larger. But inside of these parentheses right here, this is where we are starting to quantify the variation between the groups. If all of them are really close to each other, we have small values here. If they're all way far apart from each other, we have large values here. And then our mean squares for groups equals our sum of squares for groups divided by our degrees of freedom. Or if we go back up to our table, 3.994 divided by 2 is where we get that 1.997. So our mean squares for groups, this is where we have quantified the variation between groups. So that 1.997 number, that number has quantified the variation between groups. Now our error line. This is always called error. This just deals with the random variation that shows up inside of each group. Our degrees of freedom here is big N minus K. So we have 384 total people, total students in our sample, minus our 3 groups. 384 minus 3 is where we get our 381. Our sum of squared errors, this SSE. Again, we have a sum. Again, we have a square. Again, we have a scaling factor. We won't talk about why it's n sub I minus 1. But the important part here is this s, and I guess more specifically s squared. back in chapter 3, when we talked about our standard deviation and our variance, and I said, we'll use the standard deviation more often. The variance might come up in a little bit later, but the fact that we are squaring our standard deviation, we are dealing with our variances here, and our standard deviation and our variance deal with the variability that shows up within each data set. It talks about the spread inside of each data set. So right here is where we are starting to calculate, where we are starting to quantify the variation within each group. Our mean squared error, how we calculate this 0.299, that equals 113.775 divided by 381. So our sum of squared errors divided by our degrees of freedom. And then this number is our variation within groups. And that is all tied to that S or S squared that we have right there. So our variation between groups starts inside of our parentheses here. Our variation within groups deals with our S or our S squared there. This number quantifies the variation between groups. This number quantifies the variation within groups. On the previous page, we said that our S statistic is the difference, or it is the quotient between the variation between groups and the variation within groups, which means if we go back up here, how we find our F statistic, it equals 1.997 divided by 0.299. So I went through that fast. I will tell you, I am not going to quiz you on the inner workings of an ANOVA table. I will not quiz you on anything that shows up inside this table. What you do need to know is this, that our S statistic relates the variation between the groups to the variation within the groups. And if the variation between the groups gets larger, as these differences get larger, our F statistic goes up. As the variation within groups, just the random variability, as that goes up, our F statistic will go down. So in our ANOVA, we found that there was a significant difference, that at least one difference exists. We can't say smart students sit in the front, we can't say dumb students sit in the back. The only thing that we can say is not all population means are equal. So if we have significance in our ANOVA, the next logical question would be, well, where are the differences? Is there a difference between front and middle? Is there a difference between front and back? Is there a difference between middle and back? And because we're talking about differences, we're back to talking about these things 2 at a time. And if we have 6 groups, that's 15 comparisons that we have to make. That's 15 confidence intervals or 15 hypothesis tests, which at the very beginning of this chapter we're like, no, we don't want to do that. That's why we have the ANOVA. But if we find significance in our ANOVA, we do have to do that. I will tell you, it's not all that daunting though, because on SPSS, we can run what's called a post hoc analysis. And what that will do is it will find a confidence interval and it will perform a hypothesis test for all combinations of the groups 2 at a time. So in one nice table, it'll say, let's compare group 1 to group 2. Here's your confidence interval. Here's your test statistic of the hypothesis test. Here's your p-value. So we can check our confidence interval to see once if 0 is in there. We can check our p-value from our hypothesis test to see once if it's less than 0.05, and that will tell us where there are differences. So you will not have to do any of this for me. What you do need to know is what our F statistic tells us, and then Lab 8 will go over how we can do this on SPSS.